So Peter already did most of the job for me beforehand, so I'm going to go straight to the point, introduce our first speaker. He's a theoretical neuroscientist and an authority on brain imaging. His research is focused on models of functional integration in the human brain and the principles that underlie neuronal interactions. He's a professor at the University of College London, and the title of his talk is Active Inference and Deep Generative Models. I would like to give a warming welcome to Karl Friston.
It's particularly nice to be invited by students. It's the one sort of invitation you never turn down. Even nicer to be in such a lovely city and a perfect location. Must be the best venue for a conference I've ever enjoyed. So what I thought we'd start with is an overview of the free energy principle as it applies to the interests of this meeting. So looking at the remit of this conference, I've chosen to give one of the most difficult talks, so this is not the best talk I can give, but it's, I think, most appropriate for the issues at hand. We've all heard about deep learning. Yes? Hello? Hello? Should I start again? We've all heard about deep learning. What I'm going to talk about is deep inference, with a twist. It's deep inference where the depth and the hierarchical structure of the generative models that underlie action perception not only have a hierarchical structure in terms of abstraction, but also over time. So that's the basic theme that we're going to sort of work towards. I start this talk by asking some very basic questions about what it is that brains do, and we're going to address that in terms of active inference and self-evidencing. Take a little bit of time just to rehearse the kinds of models that we use to provide proof of principle, toy simulations to show what sorts of behaviours arise from the version of these generative models. There's going to be an emphasis on the distinction between the principles, the optimization principles that might provide an explanation for action and perception, and the neuronal process theories that comply with those principles. So I'm briefly going to go through, just illustrate the kinds of neuronal processes and behaviors that one can simulate if one commits to a first principle account. Cover that in terms of empirical predictions, and then conclude with a demonstration of deep inference using a form of language and reading, and again concluding with an illustration of empirical responses that one might expect to see and that one can simulate under these kinds of schemes. So let me start by asking you a question. You have to imagine you're an owl, a predatory bird, and you're hungry. So what are you going to do? What are you going to do? You're going to look around and say, brilliant. Have you seen this talk before? Perfect answer. So that's exactly what you're going to do. You're going to fly around looking for your prey. And there's a little prey worrying about being predated. That answer has a lot of implications for the way that we might formulate optimal behaviour. And I want to compare and contrast two different approaches using that specific answer. And I'm deliberately going to make a distinction between behaviours based upon value functions of the states of the world and choosing controls or policies or behaviours that maximise a function of beliefs about states of the world, a function of a function of a function. Now, I'm doing this deliberately to try and contrast the two. Later on, we'll actually repair the dichotomy and show that the first is actually a special case of the second, and explain what special conditions are required to make the first a special case. So, one approach, optimal action, depends upon the states of the world. So, if I have, give me a pointer. Perhaps I can use I can use this. We have, oh no, I don't know what it is. Thank you very much. We have this setup here, where we have a function of the state of the world that would ensue if I took this action u at this particular time. And if I can find the u that maximizes the value of these states, then I can create a state action policy. So pi for policy here, a function of each state that tells me which action to take to maximize the value of the next state. However, the very notion that we're looking for food requires you to consider beliefs about where the prey is. So a more formal way of stating searching is that you want to reduce your uncertainty about where your prey exists. As soon as you phrase it like that, it becomes apparent that what you're actually doing is optimizing a function of your beliefs, because uncertainty is an attribute of beliefs. It's not an attribute of the state of the world, it's an attribute of your beliefs about the state of the world. That tells you immediately that the appropriate action to take is that which is a function of beliefs about states of the world, that I'm going to denote by Q. They're going to become approximate posterior beliefs about states of the world, given a particular action. Furthermore, it matters the order in which I perform certain actions. So if I try to eat the prey and then search for it, I have a very different outcome than if I search for it and then eat it. And this brings to the table the notion of sequential policy optimization. So it's not just the value of the beliefs about states, or the functional beliefs about states. It's going to be a succession of functionals of beliefs over time, given a particular policy that entails a sequence of behaviors. And this is a very different construction. What it says is there is one good policy, one good sequence of behaviors that maximize this path integral or time average here, and that will prescribe the best behavior. So, two very different constructions coming under the rubric, or can be summarized in terms of these two fundamental principles. We can either appeal to Bellman's optimality principle if we think we can describe good behavior as a value, as a function of states, and from that we can derive more control theory, dynamic programming, deep reinforcement learning, economics expected utility, and so on. This class of optimization schemes appeals to Hamilton's principle of least action in the sense that if this is an energy functional, then this time integral here becomes an action, and we want to optimize the principle of most action, or at least stationary action. And this leads to things like the energy principle, active inference, artificial curiosity, and in robotics, intrinsic motivation, Bayesian decision theory, and so on. So I want to compare and contrast the two and understand what the difference is and what the implications are for schemes and message passing in the brain. I'm going to immediately just give you what I think the answer is under the second sort, and then motivate it post hoc. So this is the scheme that I'm going to be talking about. We refer to this as active inference. It's a corollary of the variation, the principle of minimizing this function or functional of beliefs about states of the world that is in fact a variation of free energy. And I should say it's exactly the same quantity used in machine learning, where it's known as an evidence lower bound. And the idea is that we can cast all behavior and all perception in terms of maximizing Bayesian model evidence, or the marginal likelihood of outcomes under a generative model of how those outcomes were caused. And that's the statisticians and machine learning people, the goodness of, or the quality of that inference is scored by this evidence lower bound. So this suggests the following architecture. We have observations from the world, and then they're taken to maximize this evidence lower bound, this free energy functional of the outcomes, that comprises two terms. So the evidence, and we'll see this in a bit more detail in the next slide, the evidence for any model has two parts to it. There's an accuracy part, how accurately, how good an explanation do I have of the actual observed outcomes here in terms of the hidden states or the causes of those consequences. But there's another term here, which is a complexity. It's just the difference between our approximate posterior and our prior beliefs. So how much I've had to move my prior beliefs about the causes to the posterior beliefs after seeing the observations. And the more I move, the more degrees of freedom I use up, and the more complex my explanation. And my job is to maximize this evidence lower bound, which means to find an accurate explanation of the data that is as simple as possible, that has a minimum complexity. And once I can do that, then I can evaluate the state of the world now and in the future under each policy. And here's the important bit. I can now, using these beliefs, evaluate the goodness of each policy. So this is essentially planning as inference. It's just saying, I'm converting the problem of choosing the next best move or behavior into an inference problem by saying, I now have beliefs about the policies that I am pursuing, and the policy that is most likely is the one that's going to be responsible for my next behavior or my next action. So what are we trying to do in this instance? Well, we're trying to maximize this evidence lower bound expected in the future. So we literally take this quantity and take the expectation under the observations that have yet to appear. And interestingly, what happens is that this complexity term becomes risk, and this accuracy term becomes ambiguity, which simply means that the good policies are those that minimize risk, where risk is the difference between what I predict will happen and what I prefer. At the same time, I'm minimizing ambiguity, namely the uncertainty about observations given I knew their causes. If I can now form beliefs about policies, I can then sample my action from the most likely policy. The action changes states in the world, those states produce new observations, and so the cycle continues. So effectively, planning as inference with two parts: beliefs about states of the world under different policies obtained by maximizing variation-free energy, and then policy selection based upon beliefs about the policy that result from maximizing expected free energy. So I'm hoping this is not too technical. This is the last slide with lots of equations on it. I think it's useful just to see how simple this construction is, and also how it relates to things that you will be more familiar with, or some of you at least will be much more familiar with. So I've unpacked this variational free energy function here in a number of different ways, so you can see how they are simply different ways of looking at the same thing. And then what we're going to do is to take components off the table and see what is left. And ultimately we're going to get back to reward learning. So here's this free energy functional here. We've already seen that it can be decomposed into complexity and accuracy. I repeat, the complexity is the difference between our posterior and prior beliefs, and the accuracy is the expected log likelihood. But I can just switch these terms around and rearrange them. This rearrangement explains why it's called an evidence lower bound. So here we have the log evidence. This is, if you like, the holy grail of Bayesian modeling. It's to maximize the probability of some data observations given a model. And what we're left with is this KL divergence between our approximate beliefs about states of the world and the true posterior of those states given some observations. And if we're going to be maximising this, we're minimising this, and this cannot be less than 0. So when we've minimised it and this is 0, then this evidence low bound then becomes the log evidence. So that's the basic construction, due to many people, but most famously Richard Feynman in his pathological formulation, converting an almost impossible integration problem into an easy optimization problem. I've written that I have expressed the evidence low bound in this form because if I now take the average of these values under a particular policy, we can now see the mapping between what's these components for any given observation now and the expected value under particular policies in the future. So the complexity becomes risk. So I'm minimizing complexity, and my expected complexity is risk. It's the difference between what I predict and what I a priori prefer. The accuracy becomes ambiguity, and then inaccuracy becomes ambiguity, which means that I'm going to choose those policies that bring me close to where I a priori think I should be, the sorts of outcomes that I expect myself to experience, while at the same time choosing to look at the world or move to perspectives on the world that are unambiguous. Right? If I was in a dark room, I'd switch the light on, so that there's a tight mapping between my observations and underlying causes. Another way of taking or looking at these expectations is if we take the evidence bound of the log evidence. So if we take the average log evidence and we associate prior beliefs about outcomes with the things that I like to observe, then this becomes an expected value or an extrinsic value. And the bound becomes an intrinsic value. Essentially, it's the KL divergence between beliefs about the world, if I saw that, relative to without seeing that. So, another way of looking at that is the information game. If I looked over there, how much information would I gain about my beliefs about what's causing my sensory impressions? Sometimes referred to as epistemic value. This is the intrinsic motivation in robotics. It's the imperative to reduce your uncertainty about what's going on out there, the states of affairs that are causing my sensations. So let me now just go through and remove a few components from this equation. Ignore this for the moment, it was meant to appear next. First of all, I'm going to remove extrinsic value. I'm going to remove any prior preferences in terms of my expected outcomes and just focus on this intrinsic value here. And I've just rearranged it to express it in terms of Bayesian surprise. So for those people in visual neurosciences who think about stochastic searches and salience maps, this is exactly the Bayesian surprise. It's the degree to which new information moves my prior beliefs to my posterior beliefs. In this instance, because we're taking an expectation about outcomes that are random variables, because they have not yet occurred, we want to maximize it. We want to maximize the information gain. This expression is just the same as the mutual information between the causes of observations in the future and the outcomes. So this is just an expression of the principle of maximum mutual information, or maximum efficiency, or the minimum redundancy principles of people like Horace Barlow. So this has a lot of construct validity in relation to established ways we think about good foraging for information, responding to epistemic value, namely epistemic affordance, in the absence of any preferences, resolving uncertainty. Now let me take a simpler case where I can see the state of the world directly. So there's no ambiguity about what I see, what the states of the world are my observations. And if I make that assumption, then I can take this away. I'm just left with these two terms. And because these states are the observations, I can write them down as a KL divergence, or a difference between my predicted states or outcomes and my prior preferences about those states or outcomes. And this is a classical objective function in optical control theory, known as KL control. In economics, it's known as risk-sensitive control, because I've removed the ambiguity. So I've removed one important source of uncertainty to reveal risk, so now we have risk-sensitive control. And if I make the final move and take all uncertainty out of the game, namely uncertainty about what would happen if I pursue this policy, we're just left with the extrinsic value. And that, of course, can be associated with expected utility theory, where there's no uncertainty or risk. And now we're back to the Bellman optimality principle. So by removing different sorts of uncertainty from the problem, we've taken the belief-based aspect out of the functional, so we don't now need the functional of beliefs. We can actually simply use the function of our preferences, expressed here as a log probability of some outcomes. So that's the basic framework. For those of you who haven't come across this epistemic value or this intrinsic motivation or intrinsic value before, this slide is just trying to make it clear what we're talking about here. So imagine that you're driving around in the night time and you're at a traffic sign here, and this can be pointing to the right or it can be pointing to the left, and you're looking over here, and you've got two policies you can pursue. You can either look over here, or you can look directly at the traffic light and disclose which direction it's pointing to. Now, if you choose the first option, you're 50-50 whether it's right or left, before you look, and also after you look. And that's true if the true state of the world is right or left. So you know exactly there's going to be absolutely no difference and no information gain and no epistemic value when comparing this posterior belief with these new outcomes with the posterior beliefs without the outcomes. And you know that exactly for every state of the world. Now contrast that with the situation where you actually look directly over here. So if the state of the world is right, then you know it's going to be right, and there's a shift in your beliefs here. Also, if the state of the world is left, then there is exactly the same KL divergence or shift in your posterior beliefs from your prior beliefs. So it doesn't matter whether we're going to the right or to the left, the information gain is exactly the same. And you know that intrinsic value is known before you make the move. So you can evaluate that before you make the move and then choose the move that has the greatest epistemic affordance or information gain. So what I'm going to do now is just briefly go through the kinds of mental models that we use to simulate the behaviours that I've just described abstractly, show you a few examples and then get to what I would like to show you in terms of deep inference. Please ignore the equations here. This is, I'm going to focus on the graphics here, just to give you a sense of how to put together these models and describe a paradigm, or in this instance, how we might explore and exploit in that little maze. So what we imagine is that there are states of the world that are generating outcomes, and they do so probabilistically via a likelihood map, usually denoted by A here. And furthermore, these states evolve in time. There's a trajectory of states whose trajectory is determined by probability transition matrices that depend upon the policy. So you, in this generative model, change the world by determining where you go from this state to the next state in time. And as we've just discussed, this policy depends upon these prior preferences, which we normally encode with a vector C over outcomes. In addition, I'm going to mention a temperature parameter or a precision inverse temperature or precision parameter that encodes the precision or confidence placed in your beliefs about the policy. We also have to have beliefs about the very first state of the world in order to generate a sequence of outcomes. And there are a couple of hyperparameters here that we need to specify in order to generate a sequence of outcomes for any given world. And once you've articulated a little universe or a little world using this partially observed Markov decision process model, you can accommodate a vast array of different games or scenarios that in principle you can then use to simulate behavior. So this is just a mathematical expression of this probabilistic graphical model here. Crucially, if you assume a simple factorized approximation to the posterior over the unknown things, then you can then turn to off-the-shelf message passing schemes that will provide the solutions that maximize that evidence lower bound that I described before. So basically do inference or simulate a little brain operating under this particular generative model, given some outcomes. And that, those off-the-shelf schemes produce solutions that are, at least to my eye, very, very simple, and more importantly, look a lot like a simplified version of a brain. So, although this looks complicated, or the previous slide looks complicated, it's not in the sense that there are just really two sorts of unknowns here, two sorts of random variables we need to infer. States of the world denoted here by the expected states of the world under a particular policy, and the policy that we're currently pursuing. And I've included here this precision parameter here, or temperature parameter beta down here, where beta is 1 over precision. So we just need to associate perception with the best expected states of the world that maximize that free energy lower bound. And that's a simple softmax function or sigmoid function of linear mixtures of observations and beliefs about states or expectations about states of the world in the past and the future. So you can think of this as a sigmoid firing voltage function of signals from other neuronal populations that are mediated by connection strengths given by the log likelihood and the log priors or probability transition matrices here. The policy selection is just a classic softmax rule where the goodness of a particular policy is the is the expected free energy scaled by its softmax parameter, where the softmax parameter is itself updated according to some a prediction error, effectively, homologous to a reward prediction error here. Updating the parameters of your priors looks exactly like Hebbian plasticity. Here there's only one sort of presynaptic component because we're talking about the initial states. We just accumulate counts by assuming Dirichlet form for these likelihoods and these priors and these initial states. If you write that down, that looks, has the same look and feel as models of experience-dependent plasticity. And then we have action selection that just takes the action from the most likely policy. And one can tell a very rough, coarse-grained story about the functional anatomy that would be required if this was the right metaphor for belief updating or message passing in the brain. Observations come in, they're used to infer states of the world in the future under different policies. They're evaluated in terms of their expected free energy with their risk and ambiguity. That leads to beliefs about policies that are selected based upon your confidence in those beliefs that then generate an outcome. You make an act upon the world, it returns another observation, and so the cycle continues. So let me just show you the kind of behaviours that arise from this formulation. This is one way of describing the generative model. We don't need to do this in any great detail, other than to say that most of the art here, most of the heavy lifting, is really thinking about the structure of the states in the world and the nature of the outcomes that we want to model or generate. So once you've worked out the outcomes that could possibly occur, then you have to write down what would I need to know in order to generate those outcomes. And then that describes the hidden states, and then once you describe the hidden states, you think about, well, if I was able to control these states, what would that look like in terms of probability transitions? So here what we're trying to do is describe a T-maze, like a two-armed bandit, well, it's actually not a two-armed bandit, it's a two-step T-maze, where a rat has to identify a location and go and retrieve a reward that can either be in the left or the right-hand side, and it's only got 2 moves. In addition, to make it interesting, there's an instructional cue at the bottom that tells it where the reward is. So the rat can either try for the right or the left, and on 50% of occasions it will get the reward and it will enjoy it for 2 moves. Or it can spend one of its moves to go and look at the instructional cue, the epistemic cue here, and then with 100% probability go and find the rewarding arm. So same expected utility or value in both cases, but this move is more epistemic. The policy where you go and get the uncertainty resolving epistemic cue that is intrinsically motivated should minimize expected free energy more because you're resolving the uncertainty, whereas you're not when you go straight for the reward. And indeed, when you simulate this, or when you invert this generative model using those equations, that's exactly what you see. So what I've shown here are a sequence of trials where the initial location of the reward is on the right and the left, and the right and the left, and then we've kept the reward at the same place. And we've enabled a learning of the initial conditions, or the context is the reward on the left or the right as time goes on. So what we see here, and these correspond to the policies, epistemic policies and then exploitative policies later on here, the reward and final outcomes. We can ignore this for the moment. The key thing about this is that initially, as expected, the rat goes and looks for the epistemic information and then uses it to secure his reward here. But as time goes on, it accumulates these Dirichlet concentration parameters and learns that the reward is always over here, which means that the epistemic affordance, or the attractiveness or the salience of this epistemic cue goes away. It ceases to be attractive because it's not resolving the same amount of uncertainty, because the rat knows that the reward is going to be on the left. Now, at a certain threshold, there's a transformation from explorative behavior to exploitative behavior, where the rat just goes straight for the rewarding cue. So, a nice and very simple illustration of the natural and deterministic progression from exploratory to exploitative behavior as the beliefs, the familiarity of this rat, its beliefs about its world change. So this is a reflection of the fact that we're now predicating optimal behavior on a function of beliefs about the rat, and beliefs about the world that change with experience and evidence accumulation here. And we can do all sorts of things with this, this kind of simulation. Here's our perception, policy selection, and the precision, the confidence part of it down here. Here's the learning again here. Same results as before, but here I've supplemented them with simulated belief updates based upon this equation, which look very much like event-related potentials that we study empirically. I plotted the belief updates according to this variational update here, and they look very much like dopamine responses. And here we saw the learning before. And now we can start to think about this, the simulated electrophysiology and how that is being mediated with this particular process theory when we go from this explorative to this exploitative mode of behavior. Basically what's happening is we have experience-dependent plasticity here that renders us much more confident, as scored by the sudden transfer, first of all, of dopamine responses from the reward to the instruction cue, and then a phase transition as we then move into these kinds of policies. accompanied by an attenuation of evoked responses, because there's less belief updating, because there's less uncertainty to resolve, and a completely different sort of behaviour. And now there's a much more reward, because the rat is able to spend 2 moves with its food as opposed to 1 move with its reward here. And we can spin out these results in many different directions. For example, we can talk about the implicit encoding of the future and the past. So one key thing of these deep generative models is that in order to plan the future, to simulate, to do planning as inference and to simulate the future, your generative model has to have representations of the future. That's the key thing. That's what we mean, or what I mean, right, by deep temporal or deep temporal generative models. Which means when you start off in a particular trial, you've already got representations of the end of the trial. And at the end of the trial, those representations now become the present, and the representations of the present at the beginning of the trial now become the past. Which means you've always got a form of prospective or retrospective memory, working memory in play. You can't do your plan without that, and there's an interesting transition from prospective memory to retrospective or post-dictive memory as time progresses here. And with that construct, you can now look at the activity of units that will, as they over time, that encode the option that you will choose or will not choose. And there's a nice literature in the reward learning literature on this kind of characterization in terms of chosen versus unchosen options. You can take another perspective. You can say, well, what we've got here is a rat foraging in some spaces, some maze, so I'm going to take a place cell perspective on this, and I can go and just look at the activity of these units here and plot them as a function of where the animal is in the maze, and we can recover place cell activity of the sort that people study empirically in rats moving around. If you're a psychologist, you can look at these results through the lens of things like emission-related responses and mismatch negativities. So here we've just compared and contrasted the responses to the second trial and the last trial before the switch in policies, because the rats saw exactly the same things and did exactly the same things. So the only difference in the belief updated is due to its beliefs that are a result of experiencing this environment and becoming familiar with the contingencies in this particular environment, in a sense of familiar versus novel, or standard versus oddball. And if we look at the belief updating in terms of the posterior expectations about hidden states, we can indeed see there's more belief updating initially, say an oddball response, relative to later on, say a standard response, producing a characteristic difference waveform that one can associate with things like the mismatch negativity. You can also play the same game with these confidence expectations that we've associated with dopamine. So on the start, we certainly know what we're going to do when we encounter the rewarding cue. But when we know what the instructional cue means, then we have a transfer of the dopamine responses to the instructional cue, which you can think of in this instance as a conditioned stimulus. So I'm just offering those examples as different perspectives on the processes that might underwrite the variational message passing, the belief updating, that all follows from, in a completely standard way, a generic generative model that itself is inverted using this one objective function, expected free energy or evidence to bound. So I'm going to finish now with where I said that I wanted to end, which is this notion of deep temporal models, deep diachronic models, and how far one can get in terms of understanding the way that we accumulate evidence, say during reading or during during language. And again, I apologize for this slide because it's not meant to be understood in any detail. It just enables me to make a very simple point. The first point is that everything I've said you can just hierarchically compose. So here you'll recognize that little Markov decision process model that I described before with states go from time 1, 2 to 3, generated time comes 1, 2 to 3, the population transition matrices dependent on the policies here that are informed by the expected free energy G here, starting with initial states. All I've done here is to take this little Markov process model here and put another one on top. And the one on top is just generating the initial conditions and doing it repeatedly. But crucially, and this is the important point, this higher level Markov decision process is operating at a slower clock time than the lower one, which means that it's generating things that don't change over the time of the lower level. For example, the policy or the likelihood matrix, or in this instance, the initial states. The initial states do not change as we move through time at the lower level. So this is what I mean by a deep generative model, and because of the separation of technical timescales, it's a sort of diachronic depth to it. That can be thought of in terms of, say, mode chunking or parsing or segmentation in language. This is a probabilistic graphical model, exactly the same as before. You just write down the equations in the usual way, relatively simple to specify. This is an exactly equivalent formulation in the form of a factor graph. And the reason I put this here is that this is what a computer scientist would use. If you gave him or her this probabilistic graphical model, he could always, using actually automated software, write down the message passing implied by this generative model in terms of this factor graph. I won't go into any details. All we're doing really is switching around nodes and edges so that now the edges now contain the messages or the sufficient statistics or beliefs that need to be passed around the various factors or nodes that correspond to our beliefs about the unknowns, the states and the policies. It's a nice way of articulating a generative model because it shows you immediately the message passing that is required in order to do the model inversion. And one sees sort of recurrent message passing into the future, and then backwards again here, as in the forwards backwards algorithm. I repeat, the key point I'm making here is if you can write down the generative model, you can get this for free. This is always specified either automatically or you can do it by hand. If you've got this, you've now got a blueprint for wiring in the brain and physiology, which means that you can now start to look at the connections and the dependencies and the direction of the messages and their time constants, and think about how would that be enacted by or implemented by a brain. And you can start to tell all sorts of stories or do jigsaw puzzles where you try to maximize the goodness of fit between this factor graph and what we know about neuroanatomy. This is just to illustrate the products of one of those games, not to be taken seriously, nor do we need to look at it, but just to illustrate, for example, that one way of mapping neuroanatomy and message passing onto that factor graph is to associate the coordinate with the evaluation of expected free energy and the precision with the globus pallidum, and we can talk about lambda-specific message passing in the prefrontal cortex in terms of these sorts of belief updates. Just an opportunity, I'm just describing here, an opportunity to get from the principles of active inference to process theories articulated in terms of a specific computational anatomy. So let me finish now with an illustration of one of these deep generative models or deep diachronic models. And it's a very elemental form of reading. So this agent doesn't actually read words, it reads pictographic or iconographic letters. So the first level of the model is basically a specification of how you would read a particular word. So words are composed of these letters, these pictures. There's a bird and a cat, and when the bird is next to the cat, that means flee. When the bird is next to the seed, it means feed, and when there's nothing next to the bird, it just means wait. And I'm considering an agent that's looking at different words. So what it will see is one of these letters: nothing, seed, bird, cat. In order to generate these outcomes, I have to know what word is currently being looked at and where in the word the agent is looking, quadrants 1, 2, 3, or 4. I'm also going to include, just for interest, another hidden cause or state here, which is flipping vertically these words. You can think of this as a manipulation of presenting letters in uppercase or in lowercase. So given I know the word, and given I know which letter it's currently being looked at, and whether the word has been flipped or not, I can always specify exactly what will be seen and what will be felt in terms of where the agent is actually looking. So this would be a sufficient and minimum generative model, or the hidden states of a generative model, for reading a letter. But I want to go a little bit further and think about reading sentences. So now we just play the same game again and elaborate this first level with the second level that moves more slowly, that sets the context for the first level. So now we have in this agent's head sentences like flee, wait, feed, wait, 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 wait and feed, and so on. So now we're considering a sequence of words where we can now move our policies at the second level on basically which word we are looking at here. And given I know the sentence and I know which word we're looking at, I now can specify which of these initial word states we are currently operating in, and then given these hidden states, I can now generate the outcomes. So we now have a deep model, very, very simple model, but a deep model that is sufficient to generate a sequence of words that is itself contextualized deeply in terms of a sequence, sequence of letters that is now also generated in terms of a sequence of words that contain those letters. And if I can write down the generative model, I just plug it into this factor formalism, use standard equations to do the inversion, and then I can simulate reading behavior. Remember, it's being driven by the resolution of uncertainty here. There are no preferences, so this is just epistemic foraging. This is just how do I go and sample the world with these eye movements to minimize my uncertainty about what would I see if I looked over there. Which sentence is in play? If I know which sentence is in play, I know which word is in play. If I know which word is in play, then I know which letter is in play. And if I know that, I know what I will see. So this is the kind of behavior that you get. It's reading this sentence: flee, wait, feed, wait. And these are the places it chooses to saccade to under that particular generative model, from word 1, 2, 3, and 4. And the key thing I wanted to show here, and these beliefs about which letter it would see if it looked over there are encoded by the images. And the idea here is that, much like real people, I'm determined to get this going. Perhaps we'll just use the top one. The key thing here is that because it can resolve uncertainty, because it gets prior knowledge about what could be out there, it actually doesn't look at everything that it could look at, very much as if when you're reading a sentence, you skip the ands and the these, and words that just do not resolve any uncertainty, because you know you're not going to get any information from them. Your eyes actually skip to the most informative next word that resolves the uncertainty. This is exactly what's happening here. So as soon as it sees cat here, it just jumps to the next word because it knows immediately this has to be a flea. And even though it doesn't actually see a letter on this word here, it jumps to the third letter, but knows that there must be this arrangement, even though it doesn't actually see anything. In other words, it has a percept in terms of its posterior beliefs about what's out there, but it's never actually gone and sampled that sensory information. It just has that percept in the absence of any sensory evidence, because it doesn't, that sensory evidence wouldn't resolve its uncertainty. And then it can accumulate beliefs about the sentence and then confirm at the end what that sentence is. So that confirmation is shown in a different form here in terms of expectations about the sentence at the top, the 6 sentences here, and the word that it is currently looking at the lower level of the model down here. And I just tried to emphasize this separation temporal timescales that you get from these deep models, iconically with these clocks here. So as we move slowly through the sentence, we're actually moving very, very quickly over the different words. So we build a beliefs about one word, and then the next word, and the next word, and the next word, accumulating beliefs about the sentences here. And notice that as soon as it sees the first word, it knows it must be sentence 1 or 4, but can only resolve uncertainty about between 1 and 4 at the end, because this is the only word that disambiguates between the two sentences. And you see the equivalent posterior expectations here about the different words that you could be looking at here as a function of times it doesn't supplant. And the reason I'm showing this the data in this format is it starts to look very much like what you'd expect to see as an electrophysiologist. So, for example, here, this is empirical recordings from monkeys looking at pre-saccadic delay period activity in the prefrontal cortex. And it starts to be reminiscent, or the simulation results start to be reminiscent here in terms of the raster, here in terms of a bar plot here, of what the neuronal activity, simulation neuroactivity looks like in this kind of scheme. In terms of electrophysiology, these are the simulated belief updates of the expected state. And again, they start to resemble perisaccadic field potentials during active vision, again recorded from monkeys here, even to the extent of looking at sort of early versus higher hierarchical level event-related potentials that have the same kind of timescale that we'd expect if the simulation was a really good description of what's going on. So I just want to finally focus on this word here, the final word, and I'm going to deliberately present stimuli that the agent wasn't expecting, just to see the different kinds of violation responses you can elicit when you have a deep model, temporally structured model, of what you think is causing your sensations. So we're going to start off. It's expecting to see this. This is the expectation that it's currently acquired through evidence accumulation. And then I'm going to do a little violation which just uses that flipping in the vertical axis, going from uppercase to lowercase. So it's expecting this, and I'm actually going to present this, and then I'm going to compare dotted versus solid lines, the expectations at the lower level, first level, so lexical expectations, and higher level semantic expectations with the red lines dotted and solid. When we look at the differences, again, as we might expect, we get a fairly early mismatch negativity-like difference waveform when comparing responses when presented with this as opposed to this. Now I'm going to do a more subtle manipulation where we're using the same stimuli, but now we're changing the semantics. So the first level can't see this, it has no representation of this, but the second level model does. So we might guess that the differences in belief updating induced by this violation of the sensory sequence will appear higher in the model and later, because it takes time for the belief updating. And remember that high levels of the model are ticking over more slowly than the lower levels of the model. And indeed, that's what we see in terms of differences here due to the global violation, the semantic violation, and we see differences in both the first and the red second level expectations, in particular a very late waveform which you could associate with, say, a P300 due to semantic violations. So that's essentially the story I wanted to tell. I'm going to close with a quote from Helmholtz, because that's what I normally do with every talk. He's one of my heroes, Richard Feynman being the other one, and Sherlock Holmes being the third. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomenon before us, that is, the existence of definite spatial relations. And what we've done here is just take that a little further and talk about spatial temporal relations in the context of deep inference. So with that, it only remains for me to thank the people whose ideas I've been talking about, and of course thank you for your attention. Thank you very much.
Okay, so we are a bit off time, but we can probably take a bit more. Questions? Who was the first one there?
First of all, thank you for the great talk and for coming. I hope I understood everything correctly and my question is not completely ridiculous now. I was wondering if you think that these rules that you wrote down and these principles like the belief updating and reducing uncertainty and free energy, if you think these need to be implemented explicitly, or if you think those are basically inherent properties of the environment that can be discovered by many different learning rules. Like, for example, if you take the experiment of the mouse in the T-shaped maze, that if I take a different learning algorithm, it would also discover that it makes sense to resolve uncertainty first and then know where to go.
That's an excellent question. In fact, there are two bits to that question. So first of all, does one need to have an explicit optimization of variation-free energy? Or is that does the environment that includes you in the environment make it look as if your dynamics and your updating and your behavior are minimizing variation-free energy or expected variation-free energy? I think the latter, so the second. So strictly speaking, the sort of the physics backstory to this more machine learning, cognitive neuroscience story would say that any system that has a self-organizes to an attracting set, which is basically defined by those prior preferences, will always look as if it is trying to optimize a variation-free energy function. That doesn't say how it's done, the physics, sorry, it doesn't tell you about the biological mechanisms or the anatomy of it, but mathematically that has to be the case. I use the word as if deliberately there. So our interpretation of self-organization can be in terms of optimizing that variation-free energy. It's a very useful interpretation, and it's particularly useful when we move from just describing systems that exist to actually building systems that self-organize for attracting self. So if you were just a biologist who was just describing self-organization in biological sciences or in the cognitive sciences, then it would be perfectly fine to say, no, things just self-organize, they have attracting sets, and it appears as though we can describe them as optimizing this slow down or variation-free energy. But when you now want to actually simulate, to make test hypotheses, or to create intelligent artifacts, for example, you now want to write down that attractance set, in which case this technology or mechanics becomes incredibly useful and necessary. So it's no longer as if, no, this simulated animal is actually optimizing through its belief updating and its behavior, the variation free energy and the expected free energy. So a subtle question and sort of an ambiguous answer depending on what your objective is. The second question, could there be a universe, a zoo, of different update rules that could produce the same optimal behavior? Yes, absolutely, but my point is, if any member of that zoo was not a special case of minimizing expected free energy, it's not fit for purpose. So the point of this is to try and say that everything that we have used and has survived in the literature for the past century is a special case of this more generic formulation. And the particular message I'm trying to get across here is that 20th century behaviorism and reinforcement learning is perfectly okay, but it's only okay if you ignore uncertainty. It just doesn't work when you have uncertainty. So in answer to your question, would you ever be able to use a deep reinforcement learning scheme to minimize uncertainty? No, you can't. There are valiant attempts to try and cast states of the world in terms of belief states, so that you change a value function of the state into a value function of the belief state, and then you can apply standard reinforcement. But the combinatorics just don't work, and you can see why immediately, because as soon as you create a state of the world that's now your belief about the world, that becomes infinite dimensional. So you can't apply standard element technology to optimizing functionals and beliefs. So my answer to the second part of the question is a little bit more clever. The point here is anything that anybody has done so far that works has to be a special case of this, and it's a special case which is rather uninteresting if they haven't got beliefs in it. So they haven't got uncertainty, epistemics, exploration as a principled approach, then it becomes less interesting for me, and I would imagine most of you, as a metaphor or a framework for understanding how we forage our worlds. Complementary answer for 10 o'clock in the morning.
So, next question.
Professor, my question is a little bit far from the framework of your today's report, but it is, as it seems to me, in your general competence. Question is, make human subjective values, exactly subjective, not in general values, subjective values, processes of thinking, those all phenomena which we call mental phenomena, be the factor of maintaining of our non-equilibrium steady states. And if may, in what way this causation by mental to physical may act in the neural networks of our brain? Thank you.
Okay, another very subtle question, which I'm not going to be able to answer in full, but I think there are answers out there. In answer to your first, or a simple response to the first question about where does subjective value fit into this framework, just practically, if I wanted to write down some subjective value, something that I valued in a sort of personal level, I'd write it down as my prior preferences. And it's important to realise that because there's nothing here which says that there is an optimal rat or an optimal human being. The idea is that if you commit to this framework, that means that there must be some prior preferences that characterise your behaviour. So it's just a way of locating how you phenotype a particular person or a particular set of wishes or beliefs about yourself. So they are encoded explicitly in the prior preferences. I won't go back to the equation, but those were the C's that we were talking about before, that will correspond most closely to preferences or cost functions that define the traits that I would see myself working towards. The second part of the question is, I think, a bit more challenging. It's how do you relate the mechanics of this belief updating to the mental and to the subjective? I think that's more philosophical. I think there are answers. If I had to look for an answer, it would be framed in terms of information geometry. It would say that, that's probably not another thing. It would say that the dynamics that we've been talking about, Hamilton's principle of least action, is one way of describing the Hamilton's principle of least action here is an apt description of these dynamics in the physical world. But the thing that's actually being optimized is a belief. And in fact, you can write down an information geometry in terms of the encoding of those beliefs, where your information geometry is not about the updates of the brain states, but the updates of the beliefs about the external states in the world causing observations. So there are two information geometries here. There's one in the self-organization of the brain and the message passing itself that follows Hamilton's principle of least action. But there's another one alongside that supervenes on exactly the same dynamics, but is articulated. It's about movements in belief space, which has a much more mental feel. It's not subjective, it doesn't talk about self-awareness, that's a whole other, I think, argument. But it certainly enables you to talk about two different sorts of beliefs, one of a probabilistic Bayesian belief propagation sort, and beliefs of a more mental sort that pertain to information geometry.
Okay, if there's a short question, one last question, because we need to proceed with the coffee break.
I don't want to delay the coffee break. I don't know if you can hear me.
I have coffee here, which is great, by the way.
So I have a rather playful, possibly a stupid question, but still. So the separation of time scale concerning your deep temporal model that you have just shown us in the last couple of slides, the separation of time scale kind of implies that the higher levels can let go of the lower levels, basically. So there cannot be, I guess, a feedback during the chain of events in the lower level. In order to separate them, you could probably allow an effect from a lower level to higher level. Now, what I want to ask is, if I trick a brain into, for example, reading a word that never ends, or is a recursive word, or something that basically would stop the whole system from proceeding, how could a higher level actually stop the lower level, for example, from going on? I think, looking at these diagrams, I could probably only solve this by giving the lower level a certain amount of clock time or something.
Yes.
So how does the brain actually do that? If I give you a riddle to solve and you figure out immediately it's a recursive riddle, for example?
Excellent question, which we could spend the entire coffee break answering. So lots of issues there. For me, the practical one is this notion of temporal scheduling. When you write down the temporal structure in generative model, how does that the scheduling and the belief updating, the message passing, mesh with a world that's actually going forward in universal clock time? And furthermore, as you say, at what point do you sort of give control back to the low level? Practically, you actually use the uncertainty perspective. You actually use an Occam's window. So when I can't resolve any more uncertainty, I give control back to the higher level again. So that's how practically we do the scheduling. But I'm not sure that's a principled answer. I think more importantly, just to note the importance of the question, the scheduling becomes incredibly important. And you're also right that, well, first of all, let's just note that the messages go in both directions. So this is like a delicate dance between hierarchical levels, where if everything is going, where there's a synchrony and a harmony between one level and its superordinate and subordinate levels, you'll get some deep inference where you'll be able to see far into the future. If, on the other hand, some horrible thing happens that was unpredictable, then basically the top levels will just collapse, and you'll be really focusing on the short term until you can start to get very precise messages passed out. So the messages from the lower level to the higher level are basically evidence for the higher level's beliefs that this is the context in which I'm operating. And I use context deliberately there because the context changes more slowly than the content. And then the reverse message passing, basically, if I know the context, I can provide good prize to you in order to work out the content. So we're in constant dialogue with each other. You're providing me evidence, no, this is the context, no, it's that context. I say, oh yes, that's good. Okay, if it's this context, then you need to look for this sort of thing. So that's why I was emphasizing that the things that are generated at the higher level, or the empirical prize that are provided in terms of top-down messages, have to be good for the duration of the cycle of the lower level. So it has to be things like the initial state. And that particular example is interesting because what it means is you have to get to the end of the first level, the lower level has to get to the end of its little horizon, its little sort of chunk of time. And then propagate its beliefs back to the beginning so that it's now updated, it's post-dicted its beliefs about where it started. And it is those post-dicted beliefs that are now inherited from the experience up to the end of its chunk of time that are then sent as evidence to the higher level. So there is actually a communication over time, but it sort of goes back upon itself to get here. And that dynamic occurs recursively, so we're also going into the future here and passing messages backwards in time. So in effect, there are vicarious conditional dependencies of lower level stuff a long way into the future, if and only if you can get that sort of message passing in synchrony, so you've got a good generative model of this actual deep structure. Otherwise, the evidence passed out will be very ambiguous and have a very high entropy, and there won't be much belief updating at the higher level, so you just won't have many precise empirical priors to contextualize your processing at the lower level. Now, a lot of really interesting work to be done in the temporal scheduling and so apart from, I think, Jeff Hawkins, I don't think there's very much work done with these deep dichotomic models at present, so the future is unknown.
Okay, so first of all, let's thank our speaker again.